we'll talk about the ECG, or as clinicians usually refer to it, the EKG, the electrocardiogram. And the K is from the Greek. It's just the old school way of referring to the electrical activity of the heart as a whole. And the reason to measure and study the ECG is that electrical activity of the heart precedes and determines the mechanical activity of the heart. So, and it's also easy to measure. As you see in the lower left, we can sort of add these electrodes to the limbs, the arms and legs, and get a recording of the ECG. And we'll talk more about that later specifically. But so it's easy to measure, and because the electrical activity the pattern of electrical activity determines the pattern of mechanical activity, it can tell us a lot about heart function. So what I want to do now is sort of give you the basis of this ECG recording. And to do so, we have to understand a couple of key things. The first one is that, and we've already seen this and done this, not physically done it, but we've talked about what an intracellular recording is, right? And so if we have a cell, right? It could be any cell. We talked about it before with neurons in AMP1. And we wanted to measure the membrane potential of this cell, right? Remember the voltage. This cell has a negative charge lined up along the inside of the membrane, and then positive charges lined up around the outside of the membrane. And again, that has to do with largely with potassium leak, right? Potassium's leaking out, making the outside more positive, and because as it leaves anions behind, it makes the inside negative. And so this separation of charge across the membrane is a voltage. And we can measure that voltage, right, by applying, it's very challenging experiment to do, right? But if we have a voltmeter, this ball with V in it is our voltmeter. Remember, voltmeter just measures voltage, right? So its job is to just measure the difference in electrical potential, the charge, between two areas. And so what we would have to do with this voltmeter to measure this membrane potential I just put a box around is put an electrode, usually glass, inside the cell, and then another one outside the cell, and the voltmeter would compare those two regions, right? And so in this scenario, the voltmeter would be measuring, in this scenario, resting membrane potential, right? And again, assuming the cell's at rest, right? And it gives us our membrane voltage or our membrane potential, same thing. Now, okay, so we talked about that. We talked about nodal cells and what type of action potentials they generate. And remember, an action potential is just a measure of the membrane voltage over time as a cell becomes stimulated, right? We also have a video on the cardiomyocytes and their action potentials. And so those are all intracellular recordings. Now, the key to this, the understanding of the ECG, is that it is derived from the action potentials of millions and millions of cardiomyocytes, not the nodal cells. The nodal cells are absolutely essential to generating the cardiomyocyte action potentials. Remember, the nodal cells fire first, the cardiomyocytes would then follow. But because the cardiomyocytes outnumber the nodal cells by 100 or 1,000 or 10,000 to 1, the majority of the electrical activity comes from the cardiomyocytes. Okay, so really we're going to focus on those cells. So the ECG is the sum of the depolarizations and repolarizations of the atrial and ventricular cardiomyocytes. Okay, so let's go back to basics though here for just a second. Let me erase this. Right? And if we look at, right, over here, what I'm erasing was one cell. Right, now let's look at a group of cells, right? So let's say this whole region here is just a big clump of cells within the heart somewhere. And notice I have the cells in one area at rest, right? Remember, let me redraw it. Right? Remember, at rest, here's a cell, and it is negative on the inside and positive on the outside at rest, right? That is our normal resting membrane potential, negative on the inside. Okay, so the ECG is the measurement of this voltage, right? This voltage was an intracellular recording, right? We were measuring the inside, this negative, relative to the outside. The ECG is not an intracellular recording. It is an extracellular recording, meaning our voltmeter is going to be out here, and I'm going to shift over to this clump of cells. Right? Here's our voltmeter again. Right? But now our electrodes are on the outside. Right? So there's one over here on the outside of cells, and we'll put another one over here on the outside of these cells. Right? And that's what these leads are down here, right? Leads 1, 2, and 3 over here are just, right? We could call this set of leads 1, 2, or 3, depending upon their location on the body. And you could also put them directly on the heart, right? Of course, you'd have to have access to the heart to do it. But okay, enough said about the leads. It's just an extracellular recording because we're comparing outside to outside, interstitial fluid charge to interstitial fluid charge, if you will. And you'll notice these cells are positive on the outside, right? Notice this positive side, positive, right? We're not even, the inside of the cell is not labeled, right? Because again, it's not that it's not negative, right? We could add that here, but are we measuring that negative? No, we're not, right? Because it's an extracellular recording. So we're comparing this positive, right, to another region down here where the positives have flooded in and left the outside of the cells more negative. In other words, this region down here is depolarized. Right? Remember, depolarized is when positive charge enters the cell and sort of negates this or cancels out this negative charge, right? Bringing the membrane potential closer to zero, right? D, or unpolarized. Whereas up at the top here, right, this area is at rest, right? We have not depolarized up here. So what that means is we have what is called a dipole, right? We have a dipole. We have a separation of charge where it's positively charged here and negatively charged here, and our voltage would not be zero. Okay? If this whole area, if this whole chunk of tissue were at rest, right, it would all be positive on the outside, right? These would all be pluses, and our voltmeter would read 0, right? And we actually have phases in the cardiac cycle when that's true. We'll talk about that in a moment when we draw it, right? But that's when it is isoelectric. Iso, again, meaning same, electric meaning charge. The same charge, right? If this is positive and this is positive, it's the same charge. Isoelectric. Okay, but so the whole basis of the ECG is that the heart is going through these cycles of depolarization and repolarization. We're only showing you one of those here. And because of that, we end up with this dipole, right? This separation of charge. Because of that, you would end up with current flow, right? The extracellular fluid is full of electrolytes and ions would flow because of it. And again, we can detect that difference in voltage between a difference in charge, I should say, between the two areas, which is a voltage, right? A voltage or a dipole, right? A dipole is a voltage. Okay, so let's go to a measurement of, let's take this voltmeter, right? And we're going to put these electrodes like on the heart, and now we're going to measure it over time, right? Not just at a particular instant like this image I have here. All right, so let's get rid of this guy for a second. And what I want to draw is the actual ECG trace. And of course, as I said before, the derivation of that comes from the individual cells of the heart, the atria and the ventricles, depolarizing and repolarizing asynchronously, right? Not together. Okay, so let's draw it out. It's very schematic here. It's not usually this clean, pretty looking. We'll draw a little bit more than one cycle. Okay, so again, ECG. And I'm going to label the waves on here as the P wave. This is known as the QRS complex. Then this is the T wave. And then we're back over to the P wave, right? Here's R again, Q, S. Okay. And again, so it's repeating. So we have more than a complete cardiac cycle here, more than one complete cycle of electrical activity of the heart. Now, where are these waves coming from? Well, again, this ECG trace comes from putting the electrodes somewhere on the body, right? So let's say we're using a very common one is lead 2, but it doesn't matter which one we pick here. Right? If we look at lead 1, we're going to put the electrodes on the left arm and the right arm, and we're going to compare the difference there, what those electrodes will measure. Now remember, you conduct electricity exceptionally well. So the electrical activity in your heart, that dipoles that are created aren't limited to within the heart muscle itself. The electrical differences are transmitted out through the highly conductive interstitial fluids of our body, right? And so we can detect these differences in potential charge across the heart, but we can detect them not just by putting electrodes on the heart, but actually by putting them out here in the limbs somewhere, because again, it's just going to, our body fluids are just going to conduct those electrical potential differences all the way to our extremities. Okay, and so let's, as I said, these waves are going to come from the individual cells doing things, right? Depolarizing and repolarizing. So right now I'm drawing the atrial cell action potential, right? And again, these are the cardiomyocytes. So this is an atrial action potential. Now, is there one cell in the atria? Of course not. There's millions, right? I'm drawing one representative action potential. And again, this would be an intracellular recording. Remember, this is intracellular. This, of course, is extracellular, right? In terms of the recording, where we're putting our electrodes for the measurement of the voltages. Right? Now, let me get the ventricular cells on here as well. Then we'll start talking about how they're lining up and why they're lining up. Right? So we have the ventricular cells on here. It's going to depolarize here and repolarize here. And then all the way out to here again. Right, and then we sort of get cut off. Okay, so that's the ventricular action potentials. Again, one representative intracellular recording. Let me add that over here. Right, so how are we going from the atrial cells and the ventricular cells depolarizing and repolarizing to this ECG trace? Well, we have to remember the conducting system, right? The SA node is at the top of the right atrium, which means the atrial cells, the atrial cardiomyocyte cells, are going to depolarize before the ventricular cells down here, right? So that's why the purple action potentials precede the ventricular red action potentials in time, right? Time is our, right? Time is going this way, right? So this is our electrical activity over time. So our SA node would have to have fired, we can put a label on it here if you want to, right? The SA node would have to have fired somewhere right about here, right? Because that's the stimulus, right? That's the stimulus for these atrial action potentials to occur. Okay, so, but, right, let me get rid of that so I can make some room here. Okay, and again, we don't need to talk about them with regard to the ECG because there's so few cells that they just don't create any deflection in the ECG trace. Okay, but now let's go back to our atrial cells here. There's not one, there's a whole bunch of them. So in other words, I'm overlapping, trying to overlap my action potentials, right? And then the same thing's true over here. We would have just multiple action potentials, not quite synchronous. You see what I'm doing here? So I'm overlapping the hundreds, and I've got 4 or 5. But remember, it would be probably millions of individual cells, not quite in synchrony. So some action potentials, right, these early lines, some action potentials occurring before later action potentials that would be over here, a little bit later, starting and depolarizing, going upward there, right? And so, okay, so in between that region, right, where I have some depolarized, the early ones here, and some not over here, we have a dipole. If we have a dipole, we have a voltage. If we have a voltage and we have our electrodes on our body, right, we are going to get a wave, right? Sorry, that line's not quite straight there, but right. But so atrial depolarization corresponds with the P wave. Go over here, right? And let's not skip over it. When all of the cells are depolarized, right? Remember, if all the cells are depolarized, there's no difference between the outside of the cells in those two regions, right? Across the atrial chambers, which means there is no dipole and there is no wave, right? These are called segments, right? So the PR segment looks like PQ, but they call it PR because R is easier to measure, right? But this PR segment here in blue refers to and corresponds with when all of the atrial cells are depolarized, right? In other words, it's isoelectric, the same charge. They're all depolarized. So same charge, isoelectric. Now, recall that in the atrial action potential, that means there's calcium influx. Calcium is the stimulus for muscle contraction. And so the atrial contraction actually occurs, the majority of it occurs during this PR segment. Aha! The electrical activity is telling us about the mechanical activity, right? In this segment here, we're fully depolarized, so we're contracting. Then with these cells start to repolarize. Do they do it all at the exact same instant? Nope, right? Some do it early here, some do it late over here. In between, we have some that are and some that are not repolarized. And of course, that is going to correspond with this wave, right? The QRS complex. Okay? And again, we get over here to the other one that we drew, and it's the exact same thing, right? The depolarization of the atria corresponds with the P wave. The repolarization corresponds with the QRS complex. Okay. Good with atria. Let's go to the ventricles. Right? In the ventricles, the action potential occurs later, as I said previously, because it takes time to go across the stimulus, the depolarization, to cross the AV node and through the fibrous skeleton, through the AV bundle and into the ventricles. And so we have this delay, an intentional, right, adaptive delay, so that the atria can contract and help fill the ventricles before the ventricles are stimulated to contract, right? their action potential. So, but of course, we don't have one ventricular cell. We have millions and millions of them, right? And again, not showing you millions and millions here. But and it's the same deal. When it's in this span where we have all these lines right here, right? We have some that went early, some that went a little later, and in between, we have a dipole. And so I'm going to draw this arrow up here too, to the QRS complex. Now, everyone says that the QRS complex corresponds with ventricular depolarization, the arrow I just drew here, right? Although I said before that the atrial repolarization is part of this as well. That is absolutely true. So why are we saying the ventricles are the rationale for the QRS complex? The ventricles are 10 times the size of the atria. That means they contribute 10 times as much to this QRS wave, right? So everybody sort of negates or sort of, forgets about this atrial repolarization being part of it. You should know that it occurs during this time frame, but is it really contributing, to the majority of this QRS complex? No, it's not. Okay. Now, then all of the ventricular cells would be depolarized at the same time. Check it out. Another isoelectric line. Right, same charge. Everybody's depolarized, so it's flat. Right? Does it mean that the heart's doing nothing? No, it doesn't. Right? It's electrically in the same state across the heart because that's everything's depolarized. Right? It's not changing, I should say. Right? Everybody's at the same state. They're all depolarized. However, right, that also means that the ventricular cells are contracting. So during the PR segment, the atria were contracting, whereas during the ST segment, the ventricles are contracting. Right? Again, associated with the plateau and the calcium influx. Plateau in the action potential here. Right? Let's come over to our ventricular repolarization. This is a less synchronous event, right? They're more spread out over time, right? Early ones are repolarizing, late ones have not, again, when we're in between here somewhere, right? Some are and some are not repolarized, and so the T wave corresponds with ventricular repolarization. Okay, now you may ask the question, or you might not think of this, but remember the P wave was depolarization. The QRS wave was largely depolarization, right? Remember the ventricular depolarization. The T wave is repolarization. Why is it up? Right? It's also an upward deflection. That seems weird. It should go down, right? Because it's an oppositely directed electrical change. It's a repolarization, not a depolarization. It's a complicated answer, but we'll just sort of simplify it here and say that if depolarization occurs from A to B, then you would think that repolarization would occur from A to B, right? Whatever depolarizes first should repolarize first. That's not true in the ventricle. And the reason that's not true in the ventricle is that the duration of the action potentials differs from region to region. And so what it means is what depolarizes first actually repolarizes last, not first. And that flips this wave. Okay? Minor detail, but I did want to point out that it does explain this sort of anomalous upward deflection of the T wave. Okay. Again, we'll stay away from any scary details on that. Okay, we're not quite done yet, right? Because we have this, after the T wave, before our next P wave, we have this TP segment. Right here. Right? That's isoelectric. But why is it isoelectric? Check it out. The atria are at rest. The ventricles are at rest, right? Which means that they are not contracting. So in this scenario, in the TP segment, right, we're isoelectric, but our chambers are not contracting. Remember, in the PR segment over here, right? This is the PR segment right here. The atria were contracting. In the ST segment here, the ventricles were contracting. And lastly, in the TP segment here, nobody is contracting. Everybody is at rest, which means that you can't just lump all of the isoelectric lines into the same sort of category. During two of them, we're getting contraction. Atrial during the first here, ventricles in the second, ST segment. But in the TP segment, we're isoelectric for a different reason. We're isoelectric because nobody is depolarized. And again, that's going to mean that the outside of the cells are the same, right, in all regions of the heart, which means we have no dipole and we would have no wave. Right? But that, of course, is opposite than being completely depolarized as we were here or here, right, during the plateau of either the atrial or ventricular cardiomyocytes. Okay, now in the Wiggers diagram, in a separate video, we will correlate these depolarizations, right, to the contractions and pressure generation of the ventricles. That is sort of the next key step. But in this video, we wanted to focus simply on what generates the ECG, what the sequence of events are, right, because this tells us about the cardiac cycle. This P, QRS, and T waves tell us that the atria are going first and the ventricles are going second. And it also explains this sort of derivation from, right? You can memorize those waves, but it's better if you understand those waves in terms of the atrial cell depolarizations and the ventricular cell depolarizations, because again, the goal for us is to make sure you understand how the electrical is the determinant for the mechanical, right? Understanding just an electrical event, you know, identifying just an electrical event and not knowing how it correlates to the mechanical event is essentially useless, right? The mechanical events are the key. That's what moves blood, right? Measuring the ECG is important because it tells us about the it is the measurement of the electrical events, but it tells us about the mechanical ones. All right. Till next time.